just in case anybody's absent, I'll record this. So what we're doing is we're drawing the free body diagrams, deciding whether the acceleration is 0 or is not 0, and that means whether the net force is 0 or is not 0, and then writing the summation equations in the x direction and the y direction. Okay. If you don't have a printer to print this out, you don't have to print it out, but I would recommend making a little sketch of the picture, right? So it's not too hard to make a little sketch of the picture. You write, like, draw a little bird, you write he's motionless, right? So that would be some important information. Free body diagram. Free body diagrams start off as a box. So you just draw a box. What forces are pushing or pulling on our bird? What's the obvious one? Obvious one is gravity. Gravity goes straight down. Is this force of gravity 9.8? Why not? That's the acceleration caused by gravity, but that's not the force of gravity. So how do we calculate the force of gravity if we wanted to? Mass times 9.8. Is the bird falling? So what does that mean? What does that tell us? It means there has to be some force pushing up against our bird so that it doesn't fall, right? And we have a special name for that force. So anytime our object is on a surface, it's supported by some sort of surface, we call that the normal force. And this sheet is available also in Schoology in yesterday's folder, because once I got access to the internet, I could record it. It says my internet is unstable. That's okay. If y'all kick out, I am recording this. Or if I kick out for whatever reason on the Zoom, this will be recorded, and the recording is not dependent on the internet. So that's good. The reason we call it normal, it's not because it's typical, it's not because it's regular, it's not because it's average. Normal in physics means perpendicular. So by saying this is the normal force, we're saying this is the perpendicular force. And it's always perpendicular to the surface. So on our free body diagram, we can label that Fn for normal. Are there any other forces pushing or pulling on our bird? Anything pushing on our bird from the side? Pulling our bird from the side? Nope. So that's the end of our free body diagram. So now over here, is our bird moving? Nope. Direction of motion? None. Is our bird accelerating? Nope. So what does that mean for the acceleration? Equals 0. What about the net force? If the acceleration is 0, what does that mean for our net force? It also equals 0, right? Our net force is also the sum of all the forces, equals mass times acceleration. If the acceleration is 0, 0 times anything is 0. So, summation equations. In the x direction, are there any forces? Nope. In the y direction, are there any forces? Yep. So, we got to make sure we keep in mind what's going up and what's going down. What's going up? The normal force. And what's going down? Force of gravity. What if this bird had a mass of, let's say, half a kilogram? That's still a really heavy bird, but it's a big bird. What would the force of gravity be on that bird? We would take 0.5 and multiply it by what? Would we use 9.81 or would we use negative 9.81? So in this case, we've already got the direction over here. So that means if we've got the direction in our summation equation, this should be positive 9.81 that we use to multiply. Okay? If we use the negative over here, then all of a sudden we'll have a negative minus another negative, which winds up being positive. That's not what we want. The negative is to help us keep track of the direction. So if it's negative over here, we don't need to make it negative over here, because we already took care of which direction it's going. So you can write a little note. Positive because FG is negative over here. Right. Remember when you're taking notes that it is important to write down the explanation for why things are the way they are. Sometimes I don't always write down the explanation as I explain things. But if you're like, oh, that's a good explanation, I understand that now, make sure that goes in your notes. Any questions with this one? Online students? Any questions? Silence means y'all understand. Alright, so the next one is a hockey player. So try to draw the free body diagram real quick. Do the equal 0, not equal to 0, do the summation equation. Alright. Are you all ready? So free body diagrams always start out as a box. What is definitely pulling on the hockey player? He's on what planet? Earth, so there's definitely gravity. Pretty much always, you can always start off with gravity. Is he standing on a surface, resting on a surface, sitting on a surface, leaning against a surface? Yes, the ice, right? So if there's a surface involved that he's standing on, sitting on, resting on, leaning on, what does that mean? Normal force. Which way is the normal force going to go? Up? Why up? Why up? What does normal mean in physics? Normal means perpendicular. Perpendicular to the surface. So if we can assume that the hockey rink is fairly flat, so that means the normal force is straight up. Are there any horizontal forces pushing or pulling on our hockey player? What do y'all think? I see some yeses. Do I see any no's? What is our hockey player doing? What kind of surface is this? This is ice, right? Ice is one of the key words to imply frictionless. So even if it doesn't say frictionless ice, if it says ice, assume it's frictionless. Ice is one of those little kind of sneaky keywords to be like, there is no friction. It's slippery enough that you don't have to worry about it. Another word that would be similar to ice would be like a very smooth surface. If you see ice or very smooth, that means there's no friction. So we know there's no friction. It's frictionless ice. Is there anything pushing him forward? So there's nothing to kind of slow him down, at least not just in a regular basis. Is there anything making him get faster or get slower other than friction? Why do you say no? Yeah. This part here is important. He's moving at a constant velocity. So constant velocity tells us there's no outside force to make him get faster. There's no outside force to make him get slower. So in this case, even though he's moving at a constant speed. So this is our free body diagram. If he's moving, let's say he's moving this way. So which way, what's his direction of motion? Positive or negative? Positive. Is he accelerating? Not accelerating. So that means acceleration is 0 or is not 0? Is 0. No acceleration means 0 acceleration. So that means the net force is also 0. In the x direction, are there any forces? Nope. Big 0. In the y direction? Fn minus Fg. Any questions with that one? Are y'all okay that he's moving but there's no force on him? Like, what if... So, the ice skater was already moving when we started watching him, is pretty much what this is, right? Kind of like when we had... When we throw something and it goes through the air, we don't care about when it's in our hand. We only care about it right after it leaves our hand and it's already moving, or right before we catch it and it's not stopped. Same thing with the hockey player. He already started going and now he's just sliding across the ice. Does that help? Okay, next. So try the free body diagram for the baseball player who is sliding into base. And just like the hockey player who was already going, the baseball player is already all the way on the ground sliding into base. So he's not falling into base anymore, he is just doing the sliding part. Make sure you make a little sketch of this into your notes if you don't have the paper printed out. Write a little bit about the situation. He slows as he slides into base. Free body diagrams always start out as a box. What force is definitely pulling on the baseball player? Definitely gravity. Gravity goes straight down. Is he on a surface of some sort? Is the surface mostly horizontal? So that means that the normal force goes straight up because that is perpendicular to our surface. Are there any other forces pushing or pulling on our baseball player? Friction is definitely pulling on our baseball player this time. if he is sliding into base this way, like the picture shows, which way does friction have to be to slow him down? It has to be the other way, right? If we wanted to be, I'm okay with just putting FF for force of friction, but friction does have, we can be a little bit more specific with friction. It can either be kinetic friction or static friction. Kinetic friction is for when something is already sliding. Static friction is for when you're pushing against something, but it's not moving yet. What kind of friction does the baseball player have? Kinetic friction. So if you wanted to be more specific, you could say kinetic. Are there any other forces pushing or pulling on our baseball player? What do y'all think? Nothing else. That's correct. So this is it. He was already moving forward, so there is no forward, like once you're sliding on the ground into base, it's kind of hard to like propel yourself forward, right? You're not going to doggy paddle into base. You were already moving forward, and that is, you're going to keep moving forward until you stop because of friction, right? So what's his direction of motion? At least according to this picture. Negative. Is he accelerating? Yes. So that means the acceleration is not 0, which means the net force also is not 0. But we kind of have to be careful, because one of our directions does have 0 net force. He's not accelerating in every direction, just in one of the directions. So let's see which one. In the x direction, what forces do we have? Force of friction? Is that it? Yes. What about in the y direction? Normal force from the surface minus the force of gravity, minus because gravity is going down. Is he accelerating in the y direction? So is he accelerating up off of the ground or falling into the ground? No. So in the y direction, his acceleration and his net force are 0. He already did the falling down bit, and now he's just sliding. If we wanted to calculate some things like how much his acceleration is or how much mass he has, what would we have to do to this? What would we do? Yeah, so remember the first step is the picture. In this case, that's free body diagram. Second step is the summation equation, which is this. Our third step is using Newton's second law. And if we're accelerating, what we do is we substitute mass times acceleration for this here. Right? Do y'all remember that from yesterday? Today we're not really doing that because I wanted to focus on just drawing the picture and writing the equation. On Friday I'll be giving you a handout that has, like on the front it has draw the picture, write the equation, and on the back it has little bits of extra information for each situation so you can do some calculations. I would recommend doing those, like one of those a day over the break, because what's happening on Wednesday when we get back? The quiz. I'm not trying to, I know, like, I want to have a nice Thanksgiving break too, and I know y'all want the same thing, so. It could. Yeah, you can. Yeah, you can. There will be an example where you can have a single lone negative thing. Alright, so try for the bucket of water. But, does the bucket of water, is it being supported by a surface? There is no surface supporting the bucket. But there is an upward force on the bucket. It's not going to be called the normal force, but there is something upward on our bucket. Are y'all writing things down online, students? I see like maybe one person writing things down, and then a bunch of blank screens. Make sure you're writing things down. Okay, now ready? So a bucket of water, what is pulling on the bucket of water? Definitely gravity. Gravity goes straight down. What's pulling up on the bucket? Probably some sort of rope or cord or string or something. When we have a force from a rope, string, cord, cable, wire, chain, we call that tension. So this one would be called the force of tension. Which way is the bucket moving? Is it being, read some words. Is it moving up or moving down or just staying still? It's moving up. Is it accelerating? How do we know it's not accelerating? Constant velocity tells us in the problem itself. So that means the acceleration is or is not. Is 0, which also means the net force is 0. Any forces in the x direction? None. In the y direction, we have the force of tension going up minus the force of gravity going down. Will those also, will those combined equal 0? Like, force of tension minus force of gravity, will that equal 0? Oh man, this is a stumper. Will it equal 0? Why do you say yes? Why do you say no? I got a no from an online student. Why do you say no? Why do you say that?
Because it's actually moving.
Just because it's moving doesn't mean that it necessarily has a net force. It has no net force. Why? How is it moving? Constant velocity. The net force is 0. So, all of this, whatever this is our net force, right? So our net force has to be 0 because it's not accelerating. Oh man, I changed how I asked the question just a little bit and it stumps y'all. That's still 0. This is why there will be practice calculating things. And I encourage you to do the practice calculating things over the break, and we will do some practice together at least on Friday, for sure. Probably also other days. Any questions with this one? Y'all good with this one? Okay. I kind of want to skip the disco ball. Is there much difference between the disco ball and our bucket in the well? Not really. The disco ball isn't moving, but it's still not accelerating, right? So that means the free body diagram is the same. The acceleration is both equal to 0. The summation equations are the same. So this one's just the same, it's just staying still. Okay, skydiver. For this one, we are still assuming there is no air resistance. So we go ahead and draw a free body diagram for our skydiver. Y'all ready with the skydiver? Okay. What's pulling on the skydiver? Definitely gravity. Is he supported by a surface? Is he pulled up by ropes? Nope. Is there anything going up? Nope. Is there anything sideways? Nope. That's it. That is the free body diagram for the skydiver. Which way is our skydiver moving? Down. What about his acceleration? Is he accelerating? Yes. We dropped him out of a plane. He is accelerating. Not equal 0. Do we know how much he's accelerating? We dropped him out of a plane. Do we know the acceleration of things that are dropped on the planet Earth? Yes. How much is he accelerating? 9.81 meters per second squared. So that means the net force is not 0. Do we know the net force acting on him? Why not? Because we don't have what? The mass. Right? In order to know the net force, in this case the net force, there's only one force, the force of gravity. We would have to know his mass. Is there any forces in the x direction? Nope. In the y direction? Just the force of gravity. Force of gravity is, yeah. So, right, we can have just one force and have it just be negative. So now the skydiver opens his parachute, and we're going to assume there's air because otherwise the parachute won't work. So there has to be air for the parachute to work, and he is descending at a constant velocity. This is also called terminal speed. So when something has enough air resistance that it falls at a constant speed, that is called terminal velocity or terminal speed. For this one,
could I see the number 6? Because I think
just write it down. Write it down in notes. Goodness. Remember, this one is also going to be recorded. For number 7, it's also kind of good to make sure we know the system that we're looking at. Are we looking at just the skydiver, or are we looking at the skydiver and his parachute? And it kind of depends on how we want to solve the problem. But let's say for your free body diagram, let's have the system be the skydiver and the parachute. Okay. So for this one, because we are choosing our system as the skydiver and the parachute, that just changes a little bit. I'll show you what it would have been without as just the skydiver in a second. So we definitely have gravity pulling our skydiver down. What's keeping our skydiver and his parachute from plummeting to the ground? The air resistance in the parachute. So that's if we are including the parachute in our system. If we just had the skydiver as our system, we have the force of gravity pulling down on our skydiver. What's pulling the skydiver up? The parachute. So instead of force of air, this would be the force of tension in the ropes on the parachute. There might be a tiny amount of air resistance on the skydiver himself, but mostly it would be that force of tension from the ropes pulling him up. In this one, we don't worry about the force of tension because the ropes, in this case, when our system is the whole thing, this is an internal force. And internal forces don't cause the object to move. So every object stays in motion unless acted upon by an outside force. And you've probably experienced this, the fact that you can't use an internal force to make you move. Because have you ever been in a spinny chair and you try to make yourself spin around by just wiggling in the spinny chair? It is really, really hard, right? Because most of the time you wiggle one way, and then when you wiggle back, that you're right in the same spot, right? So trying to wiggle in a spinning chair is an internal force. You need an outside force like friction against the floor to help you spin, or pushing against the table. Then you have some outside force, either from the floor pushing on you or from the table pushing on you, and that's an outside force that will make you move. Internal forces don't make you move. What is our, which direction is our object going? Down. Is he accelerating? Not accelerating. Constant velocity. So what does that mean for his acceleration? 0 is 0. Net force is 0. Any forces in the x direction? Nope. Big 0. In the y direction, if we're using our system as the skydiver and his parachute, air resistance minus the force of gravity. Is that also equal to 0? Yes. Right? So force of gravity is air resistance minus the force of gravity should also equal 0. Because in the y direction, we are still not accelerating. We're going at a constant speed. If we're going at a constant speed, our net force should be 0. Try to do the basketball one. And it does say the basketball is in the middle of the free throw. So that means the basketball player is somewhere over here. He already tossed the ball. He's not touching the ball anymore. And the basketball is not yet touching the basket. So the basketball is in between the basketball player's hands and the basket. It's not touching either one of those. Ready for this one? So, free body diagram for the basketball. What forces are pushing or pulling on our basketball? Definitely gravity. Is there anything else pushing or pulling on our basketball? What do y'all think? Is there any force from the basketball player? I see mixed. I see some of both. Why yes, why no? He threw it. But where is it right now? It's in the middle of the air. Can he have a force on it while it's in the middle of the air? No, so there's no force on it from the basketball player. He has to touch it in order for there to be a force. Just like when we were throwing things, we didn't care about like while it was in our hand, we just cared about after it left our hand. And after it leaves our hand, we can't do anything to it. Anything else? Any other forces? Nope. This is it. So for the basketball, this is it. Once it leaves the basketball player's hands, he can't touch it. He can't have a force on it. He's not Darth Vader. Before it touches the basket, it won't have any normal force or surface force or friction or anything like that because it's not touching it. You can't have friction against something that you're not touching. Which way is it going? I don't know. Maybe positive? Positive, negative, something like that. Maybe going up, maybe going down. Is it accelerating? If we throw something through the air, is it accelerating? Yes, it is still accelerating. So that means our acceleration is not 0. Do we know how much it's accelerating? Are you sure? How much is it accelerating? 9.81 meters per second squared. Yes. And then the net force will also not be 0. But the net force, well, we'll get there. In the x direction, are there any forces? Nope. So no acceleration in the horizontal direction. This makes sense, right? That's what I was saying. It has a constant speed in the horizontal direction because there's no force in the horizontal direction. What about in the y direction? just minus the force of gravity. Do we know how much that force of gravity is? No. Why not? Because we don't have the mass. We know what the acceleration is, but we do not know what the force is until we know its mass. Alright, I'm going to help y'all through the next two because those are a little different. So for this one, free body diagram for the suitcase. And notice, so when you sketch your picture in your notes, online students, you can have it like here she is, right? Make sure you show that this is at an angle. That's important. So this is at an angle. We are just looking at the suitcase. So we are not looking at the woman and her suitcase. We want this to be an external force. So we're just looking at the external forces on that suitcase. What forces do we definitely have on that suitcase? Definitely have the force of gravity. Gravity goes straight down. Is the suitcase on a surface? Yes. So we have a normal force. Which way will the normal force go in this situation? Up, because normal in physics means perpendicular. So if our surface is horizontal, that means the normal force is vertical. What else do we have? How do you know there's friction? Well, it's not just because she's pulling it. She's pulling it, so we know we have an applied force, or a force of tension, if you want to call it a force of tension. I am not particular. Like, she could be pulling it with a rope, that's fine, and you could call it force of tension. She could be pulling it with her hand, like with the handle, and that could be the applied force, whatever you want to call it, just to make sure it's at an angle. But how do you know there's friction? There is friction, but how do you know it? It's touching the ground, and it doesn't say it's a smooth surface, it doesn't say it's icy, but there's a better reason. Let me start with let me show you maybe with the summation equation, especially the summation in the equation in the x direction. What are we going to do with that applied force in the It goes a little bit sideways and a little bit up, right? When we're writing our summation equation, what do you think we need to do to this force? Make components. If something's at an angle, you need the components. So there's a component going to the right, and there's a component going up. So we can call this the applied force in the x direction, and this is the applied force in the y direction. So in the x direction, we definitely have a force. If we just left it like that, what would our object do? What would the suitcase do? Well, I mean, it is going sideways, but it would also do something else. Right now, it's going sideways at a constant velocity. If we just have one force, what will that do? If it has a constant velocity, let's go back here for a second. If it has a constant velocity, what do we know about its acceleration? It's 0, which means that the net force has to be 0. Does this have a 0 net force? No, it does not have a 0 net force. We're going to assume that she's actually pulling it with some sort of force. Like, you can't pull something with a 0 amount of force. If there is a pull, if somebody is pulling something, it will have an amount of force. So if we leave it like this, what will the object do? It'll accelerate. So if we leave it like this, it'll accelerate. So we know there has to be something in the other direction that's keeping it from accelerating. What's keeping it from accelerating? Friction. And if you wanted to be picky, force of it's sliding, so it's kinetic friction. In the y direction, what do we have? In the y direction, we have the normal force minus the force of gravity. Is that it? Plus the applied force. And we know it's plus y because it's up. So sometimes you could apply a force and it would be partially down, right? So if you're pushing something and you're pushing it a little bit down, it could be negative. But in this case, we have plus the force applied in the y direction. Ooh, real quick, free body diagram for the squirrel. Gravity goes straight down. The surface is now this way, so how does the normal force go? Perpendicular to the surface. Is there gravity, or sorry, not gravity, is there friction on this squirrel? Yes. How do we know? If this was an icy, frictionless roof, what would happen to him? He would slide off. Is he sliding off? No. So we know there has to be friction going this way. Ooh, there's two things at angles. Do you want to calculate two sets of components? I don't. There's an easier way. What you do is you tilt your head a little bit and you look at it a little cockeyed. So that means the force of friction is only in our x direction. The normal force is only in our y direction. And it's the force of gravity that has components. And the last bit we need to know is what angle do we have? Usually we're given the angle of the slope, which means we will have the angle that's here. So when we calculate components, we would be using that angle. FGX would be the opposite side. FGY would be the adjacent side. Alright, y'all, you can have a good day.